All right, so we've learned about derivatives, and we've learned that a derivative f prime is basically defined as the limit of something, right? And back in chapter 2, we learned that limits sometimes don't exist. So it's possible to attempt to calculate a derivative and find that that limit doesn't exist. In the previous video, I talked about a derivative that was approaching infinity to give us a vertical tangent line, right? So that would be an example of of a situation where the limit, where the derivative doesn't exist. So there's a vocab term here to talk about this. A function is called differentiable at a specific number, c, we'll call it, if the derivative of the function at c exists. Okay, so differentiables, able to differentiate or able to calculate the derivative. So I want to go through some examples of points where functions are not differentiable. So the first is vertical tangents. So a vertical tangent line, an example of a picture of that might be a function that looks like this. And then maybe at this point right here, we might have a vertical tangent line. It looks like we have a pretty close to vertical tangent line there. So vertical tangents are examples of points where something is not differentiable, which is interesting. In this case, the tangent line does exist. It's just that the derivative is undefined because the slope is infinite. So that's one case. Another is corners or cusps, which are like sharp corners on curves. This is where the tangent line itself is undefined. So at this point here, the tangent line to be undefined, because what is the slope? I mean, do you want it to be like this slope, or do you want it to be this slope, right? It's kind of questionable as to what the slope should be, or should it be something in between? Instead, it's just undefined. A cusp is something similar to this corner, but where it kind of, it's like a combination of a corner and also approaching infinity. So it would look like that. Kind of like if you took two semicircles and put them next to each other, then you'd have a cusp where they meet. So those are points where something is not differentiable. By the way, examples of functions where this happens. One example of the vertical tangent is y equals x cubed. And one example of this is y equals the absolute value of x. You can probably recognize this looks kind of like an x cubed, and this looks kind of like an absolute value. Okay, so there's just some examples of when this comes up. And then a third one would be discontinuities of any kind. So even just like a removable discontinuity, that's still not differentiable, because in order to be differentiable, in order to calculate f prime, one of the parts involved in there is f of c, so the function has to be defined, right? So if the function is not defined, then you're going to have a problem. If you have a jump of some kind, whether the function is defined or not, let's say it is defined, you might have one slope that you're approaching from one side, but from the other side, if you take secant lines approaching from the other side, you can end up with a very different slope. So like with this example here, with this jump, if you approach from the right, the secant slopes would appear to be approaching 0. Whereas if you approach from the left, the secant slopes are going to be approaching infinite. And so those are different, and so you get another situation where it doesn't exist. The other discontinuity type, of course, is like a vertical asymptote, and that's another place where you just can't calculate a tangent slope. You can't calculate a derivative. Even if the function is defined, you're not going to get a defined or an existing limit there. So an example of a function where this might happen would be like a piecewise function, like that. That's the middle one there. Or something like 1 over x, where you have that vertical asymptote at 0. So one of the things you noticed about this probably, so this third one here, is that to be differentiable, and I'm going to write this down, and you should write this in your notes, because this is important. To be differentiable, a function must first be two things. One, continuous. We learned about continuity back in chapter 2. So continuity is required for differentiability. You can't calculate a tangent slope or an instantaneous rate of change unless it's continuous. But it's not enough because, as you can see in the first two examples here, these are continuous, right? With this corner and this cusp here, these are continuous at those points, at those sharp points, but and yet it's not differentiable. Same with the vertical tangent. It's continuous, but it's not differentiable. So a second thing that's required is what's called smooth. So the smooth means you don't have any of these corners or cusps. So I'm not going to define what smooth means very rigorously, but it's pretty intuitive. A smooth curve is one that doesn't make any sharp corners. Sometimes you can have something that looks like a sharp corner from far away, but if you zoom in on it, you'll find that it's actually curved. It's like a really tight curve, so you got to zoom real far before you see it. But it may actually be smooth. If you take like x to the power 200. You might see something that looks sort of like this, but the corners here are smooth, not sharp. Anyway, so those are two things that are required in order for a function to be differentiable. Even these two conditions are not actually sufficient because of this example, where it's both continuous and smooth, and yet it's got this vertical tangent line. So for now, this is not meant to be like a rule that like, if it is continuous and smooth, you can calculate the derivative. But it is, at the very least, it must be both continuous and smooth to have any hope of calculating a derivative or a tangent slope.